In this section, we're going to talk about how do we solve systems of equations. So we're going to go through two types first. We're going to talk about linear systems, and then we're going to extend it a little bit further to do nonlinear systems of equations. So when we talk about a system of linear equations, it's basically two lines that we're working with, hence linear means lines. So what we have is we're given two equations, and our goal is to see, can we find an xy value that satisfies both of the lines simultaneously? So if we think about this geometrically, we can graph our lines. There's ultimately three things that could potentially happen. So our very first case, maybe we have one line, if we graphed it, look like this. And then if we graph the second line, maybe it looks like this one. So the very first possibility is that there is one point that is an overlap between these two lines. And in this case, that would mean there is one solution to this equation or the system of equations. Okay? If that's the case, we call this a conditional equation. Right? Another possibility is that these two lines could run parallel to each other. So here's one line, here's the second. Okay. In this case, the lines will never overlap, so there is not a single point that satisfies both of the lines simultaneously. So here, there is no solution to this system. Okay. So when this happens, we call this an inconsistent system. You might also hear it called a contradiction as well because they're contradictory statements. They both can't be true. The very last case is kind of the hardest one to draw, but this is the case where you have one line and it happens to be the other line is exactly the same. So there is overlap between the two. In this case, every point on one line also satisfies the other line, so there are infinite solutions. And this is called a dependent system. Okay. So you ultimately have two methods to solve these. The first method is going to be substitution. The second method is going to be elimination. Both of them do exactly what their name says. In substitution, we're going to substitute one equation into the other. In elimination, we're going to eliminate one of the variables. Okay. So let's try both of these. We're going to start first by going through substitution. And then we're also going to see, how do I know if I'm in one of these other situations where I don't have a solution or there's infinite solutions. Okay. So for substitution, what I want to do is I'm looking for an x and y that works for both of these equations. So I want to take one variable and solve it, or one equation and solve it for one variable. So looking at this first equation, I know x minus y has to equal 2. So it's easy for me to solve for x because I can just add y to the other side. So my x coordinate has to equal y plus 2. Okay? So at this point, I've used this first equation, and I now know what x must equal. Well, in this second equation, if I'm looking for a solution to the system, these x's better be exactly the same thing. So I'm going to take this expression I just found for x, and I'm going to plug it into this other equation that I have not used. So we've used the first one. Now I also know that x plus y has to equal -2, but these x's must be the same. So I'm substituting in this expression I found for x. Okay. And what that does is it's gotten rid of my x variable, and now I just have a linear equation in y, and we know how to solve this. If I go ahead and condense these, y plus 2y plus y, I can group my like terms. So this is 2y plus 2 must equal -2. And then to solve, we just isolate the y value. So we subtract 2. This gives us 2y is -4. And then I divide both sides by 2. And this lands me at y must equal -2. So I found a single y value through this process that is going to solve this system. And now that I have this, I know I'm in the case where I have a single solution. There is one coordinate pair that satisfies both of my equations. But I need to figure out what x has to equal. And that's where I come back to my substitution. In reality, I could plug this y value into either one of these starting equations, and I could find x from there. But just from this substitution, I know that x has to equal y plus 2, and we just found out our y coordinate is -2. So I just replace it into my substitution. So this lands us back that our x has to equal 0. Okay? So we found a single point that is going to satisfy both equations. So the way we would write our solution is that our x is equal to 0 and our y is equal to -2. Or we could write it as the coordinate pair, 0, -2. Okay. You can also plug these back into the original equation and check that it satisfies both of them. Really up to you. A little bit hard to do when you run into those other situations. But this is the whole process that we have. Take one equation, solve for one variable, substitute it into the other, solve the resulting equation. Okay. Let's try another one. We're going to use substitution again, and I want to solve this system. And so I want to take one equation and I want to solve it for one variable. So really, they both look similar. I'm going to go ahead and I'm going to work with this first one. So we know 3x minus y has to equal 2. In this case, I think it's probably easier to solve for y because I don't want to get rid of that 3 attached to the x. So let's go ahead and move the 3x to the other side. My 2 just fell off. So subtract the 3x. This gives us -y has to equal 2 minus 3x. And then I'm going to go ahead and I'm going to take both sides and multiply it by -1 to give us y. And now it's going to change the signs on both of these. So I'm just going to flip the order. It's positive 3x minus 2. Okay. So I've used my first equation, and I know y has to equal this expression. So now I'm going to go to my second equation, and where I see a y, I'm going to replace it by the 3x minus 2. So from our second equation, we know that this also must be true. And we just figured out that y is 3x minus 2. So I result in an equation only involving x that I now can solve. So if we distribute that minus sign, that's minus 3x plus 2 equals 4. And now we run into a little bit of a problem because the 3x's cancel, and I end up with 2 equals 4. Okay. Because I end up with something that is never a true statement, this is that case where there is no solution to this system. Nothing is going to make this true. Okay. And really, if you look back at the start, I didn't need to do all this work to come to that conclusion. On the left-hand side, I have exactly the same thing. And on the right-hand side, I have different numbers. There's no way I can find a value that works for both of these because they are going to end up being this case where these are parallel lines. Now let's try our other process. Let's go through elimination. And so the goal here is we want to eliminate a variable. So what you want to do is you want to make it so, in this case, if I try to eliminate x, I want them to have the same number but opposite signs. So this way, if I add the equations together, I'm going to eliminate a variable. And I could do the same thing. I could choose to eliminate y. I want the same number but opposite signs so they cancel when I add them together. So you can do either one in this case, But if you look at the y values, one is positive and one is negative. So it's a little bit nicer to eliminate y. So what we're going to do is I want to get the same number out front. I want this to be negative 2y. So those cancel each other out. So what I need to do is I need to take this equation and multiply it by 2. And in doing so, that gives us 2x minus 2y equals negative 20. And then our second equation is still exactly the same. But now, because the y's have opposite values, we can cancel them out when we add them together. And then on the left-hand side, I take the 2x and the 2x to give me 4x. And on the right-hand side, negative 20 plus 16 gives me negative 4. So I've eliminated y, and I now can solve for x. Because all I need to do is take this side and divide it by 4. And now I know that my x coordinate is negative 1. And now that I have x, I just need to figure out what is y. So you can plug that into either of these original equations and find your missing variable. So I'm going to use the first. We know x minus y has to equal negative 10. We just found out x is negative 1. So I'm going to replace that in the equation, and I solve for y. So I've got to isolate y, which means we add 1 to both sides, which gives us negative 1, or negative y is negative 9. And then I got to get rid of this minus sign, so I go ahead and change the sign of everything, or think of it as multiplying by negative 1, dividing by negative 1. This gives us y is equal to positive 9. So again, we have a single point that satisfies both equations. My x is negative 1, and my y is 9. Okay? And again, I didn't have to go through this elimination process. I could have chosen to eliminate my x variable just to show you you'd still get the same thing. If I multiply this equation by negative 2, this would be negative 2x plus 2y equals positive 20. And then that would be 2x plus 2y equals 16. If we go and solve this equation, I've now got the opposite sign in front of my x, but the same number. So they cancel out. And that gives us 4y is equal to 36. And then we divide by 4, and you end up with exactly the same value for y of 9. I would plug this back into my starting equation, and then I would see that x would have to equal negative 1 to satisfy both equations. Okay? Let's try one more example, and we're going to run into this last case of we have infinite number of solutions. So again, I'm going to try to eliminate one of the variable. So looking at x from the get-go, one is positive, one is negative. If I take this top equation and I multiply it by 2, I'm going to get the same value of 10 in front of x, but opposite signs. So when I multiply that by 2, it gives us negative 10x minus 6y equals negative 2. And then our second equation is 10x plus 6y equals positive 2. And now here, some fun stuff happens when I add these together. The x's cancel, the y's also cancel, and the constants end up canceling. So really I'm left with nothing and nothing on both sides. Okay? So in our case of no solution, you end up with a false statement, but here, this is always a true statement. So no matter what you do when you try to do the system, you boil down to something that's always true. So this is a dependent system, and there are infinite solutions. So there is a very specific way that we have to go about writing these. It's called parametrically. But what we do is we want to solve one equation for one variable. So we let x be a real number. because in reality there are infinite equations, but they still have to be points on the line. So with this, if x is any real number, from the first equation, we get the following. We know negative 5x minus 3y has to equal negative 1. My x can be anything, but my y is still specific. So I'm going to go ahead and I'm going to add the 5x to both sides. So this gives us negative 3y is 5x minus 1. And then I'm going to go ahead and I'm going to take both sides and divide by negative 3. So this gives us our y is negative 5/3 x plus 1/3. So once I pick an x value, my y value must be this to be a point on the line. So the way we express our infinite number of solutions is our x can be whatever it wants, but the y value must adhere to this equation. It must equal negative 5/3 times the x coordinate plus 1/3, where x is any real number. Okay. So this is called parametrically because I'm still writing the points on the line in a very specific way. The x coordinate can be whatever it wants, but the y coordinate is dependent upon the x value because I can't just plug anything I want in and it satisfies both of them. Like if I try to plug 0, 0, that's not a point on this line, so it doesn't actually solve the system. There are still specific solutions. So we're going to get more practice with this because we're going to do 3 equations with 3 unknowns, and you really have to get it down to 2 equations and 2 unknowns. But before we do that, we want to talk about nonlinear systems. And what we mean by nonlinear is at least one of your equations is not a line. One of them could be, but the other could be a parabola, it could be a circle, it could be an absolute value. You can have a bunch of different things. So your goal is still to find points, xy coordinates, that are on both of these equations. So you're looking for points of intersection. The problem is there's not a set in stone solution to these. I can't immediately tell you that there's one, none, or infinite number. So just to give you just a few examples, maybe one of our equations is a parabola. So we have a shape that looks like this. And the other equation is a line. Right? It's still absolutely possible that there is a single point that satisfies both of those equations simultaneously. But now, if I just move this line up a tiny bit, I end up with more answers. Okay? So my first example gave us a single solution. But now, if I move the line up a tiny bit, we end up having 2 solutions for a very similar problem. So there's no way to predict it. You could try to graph this thing to try to determine that you found the correct number, but there's no set rhyme or reason. And then you can even have funkier things going on. Maybe you do still have a parabola, but then you have a circle. Okay. In this case, you have, let's see if it'll go, there we go. 1, 2, 3, 4 points of intersection, and there are 4 solutions that solve that system of equations. Okay. So you can definitely utilize like an online graphing tool to help you out to make sure you found the right number. You can use substitution on these equations, you can use elimination, but it's really just going to take a lot of practice to figure out what do you need to do. So we're going to try a single example. When I look at this equation, I don't know necessarily how to graph that bottom one, but that's okay. But immediately, because I have a y and a y squared, there is absolutely no way I can easily eliminate my y variables. So what I want to do instead is I want to try to get rid of my x to give me an equation involving y. Right? And in this case, it's actually primed up really nicely for substitution. Okay? You definitely can use elimination and eliminate the x value, but substitution also works. Because just from the second equation, my x has to equal y squared plus 1. I can just plug that in for x in this original equation, okay? So we know that 2y minus x needs to equal 0. And my x better also equal y squared plus 1. So we're going to go ahead and plug that into my equation for x. Okay. So what we ended up doing was we ended up creating a quadratic equation. So if I just rearrange this, I've got to distribute that minus sign, and then I'll put the y squared first, the y in the middle, the constant at the end. And then I also really hate that minus sign out front. So let's multiply everything by -1. And it gives us y squared minus 2y plus 1 equals 0. So I end up with a quadratic equation that I need to solve. Thankfully for this one, we can factor it really nicely as y minus 1, y minus 1. So we only end up with a single value for y. If it didn't factor so nicely, you might have two different y values, and you would have to find the x corresponding to both of them. But here, I now know that my y has to equal 1, right? So using our equation again, I need to find what x is equal to. So I need to plug this in, but we know x is y squared plus 1. So our x coordinate is going to equal 1 squared plus 1, which is just 2. So we get a single solution where our x is equal to 2 and our y is equal to 1. Okay. Here, I would definitely recommend checking them because you might end up finding something is an extraneous solution, or what tends to happen a lot of times is people start pairing a ton of things together and you create more. When you check, then you can kind of realize, oh, okay, these ones aren't really solutions. I just paired stuff that I shouldn't have together. Okay, so do your best. Take a lot of practice with these. If you're moving on to our pre-calc class, we're going to be doing this there too. So you'll get lots and lots and lots of practice with these kind of problems.